Our objective is to prove the Jordan-Holder theorem, and the path that we'll take towards the Jordan-Holder theorem is via a theorem called Schreier's theorem, which is a very general theorem with no assumptions on the ring R whose modules we are considering. So let's look at Schreier's theorem. So firstly, before we do that, I need to make one more definition about the equivalence of two composition series. So two composition series, let's say the first one is mi, I goes from 0 to m, and the second one nj, j goes from 0 to n, are said to be equivalent basically if their quotients are the same. More precisely, if firstly m is equal to n, and secondly there exists a permutation let's call it sigma from the set 0 to m minus 1 to the set 0 to n minus 1, such that the quotient corresponding to I, let's say mi mod mi plus 1, is isomorphic to the quotient corresponding to sigma I in the second composition series. So n sigma I mod n sigma I plus 1 for each I in 1 to in the range 1 to m minus 1. Okay, so two composition series are equivalent if their quotients are the same. So last time we had looked at an example of composition series. We started with the ring R to be Z, and we looked at the R module M equals Z mod 12Z. And we had listed firstly all the submodules of this module, and then using that we had also listed the composition series. And in red here I have also the quotients listed. The integer I means I'm looking at Z mod IZ as the quotient. So there was a small mistake here. This 2 and 6 need to be interchanged. I don't know if you noticed it. This is 6 and this is 2. Okay. So now if you see all these three things here in the last, these are equivalent. This is equivalent to this is equivalent to this, because there are three quotients. Two of them are Z mod 2 and one of them is Z mod 3. So you can permute these things and get these. But over here, what we have is that this is equivalent to this, and these two, this composition series is equivalent to this composition series. Okay, so we have two equivalence classes for composition series with n equals 2, and we have a single equivalence class with composition series with n equals 3. In fact, this last thing, that all the composition series of the longest length, which turn out to be Jordan-Holder series, are all equivalent, is the Jordan-Holder theorem. Okay, but in any case, what you see here is that given any two series, composition series, there is, for example, you could take 2, 6, and for these two series, this is a common refinement. Whereas if you take this series and this series, the first and third in this second row, that is m contains 2, m contains 0, and m contains 3, m contains 0, they do not have a common refinement. However, they both have refinements which are equivalent. And that's basically the content of Schreier's theorem. So let's state Schreier's theorem. Any two composition series sigma 1 and sigma 2 of an R module M admit refinements let's call them sigma 1 prime and sigma 2 prime. That means sigma 1 prime is a refinement of sigma 1 and sigma 2 prime is a refinement of sigma 2. So let's write respectively such that are equivalent. And we saw how this works in the example of Z mod 12. The proof of Schreier's theorem rests upon a very simple idea. So let me explain the idea to you. So firstly, let's give these composition series names. So we have, let's say sigma 1 is just the series mi, I goes from 0 to m. And let's say sigma 2 is the series nj, j goes from 0 to n. Now the idea behind the proof is use sigma 2 to define sigma 1 and use sigma 1 to define sigma 2. So these will give rise to refinements sigma 1 prime and sigma 2 prime, and we will show that these refinements are actually equivalent. So how do we do this? So let's start with firstly refining sigma 1 using sigma 2. Okay, so let's start with sigma 2 itself. So sigma 2 is this thing. So you start n0 is m, and then that contains n1, that contains, and so on, all the way down to nn, which is equal to 0. Okay, now let's take this and intersect it with mi. So I get mi is equal to mi intersect n0, which contains mi intersect n1 all the way to mi intersect nn, which is 0. But this is not what I want. I don't want to go refine. I want to refine the sigma 1, which is the m's. So I don't want to end up at 0 here. I want to end up at mi plus 1. So what I'll do is I'll add mi plus 1 to each of these things. So the next step is we have mi, but let's just add mi plus 1 to all these modules. So this is the same as mi plus 1 plus mi intersect n0, and that contains mi plus 1 plus mi intersect n1, and so on. And finally we have mi plus 1 plus mi intersect nn. Okay, and this last term is equal to mi plus 1. Now in this refinement, it's quite possible, so this is actually a refinement of m. Let me write it down more explicitly, but it's quite possible that many of these terms here are going to coincide with each other. There'll be no change between this module here and the next module. It's quite possible that that will often happen. So we are not talking about strict strict composition series here. We're just talking about composition series where terms are allowed to repeat. So finally what we get is this composition series sigma 1 prime. So sigma 1 prime, let's just say let sigma 1 prime be the composition series. So given by Mij equal to Mi plus 1 plus Mi intersect Nj. So what we write is, so first we start with M equal to M0, 0, and that contains M0, 1, that contains M0, 2. So here now J is changing as we had in each row of this here, right? So J is changing as we had in each row over here, and this goes all the way up to M0 n, and this is equal to M1. Okay, and so that's again we go on now to the next terms, which is so M1 is still equal to M10, which contains M11, which contains M12, and so on, which goes down to M1n, which is now equal to M2, and this is equal to M20, and so on. And finally we'll end up with all the way down to Mn, which is 0. So this sigma 1 is this composition series given by this, and we have two indices. We take I goes from 1 to n, and j goes from 1 to m, 0 to m. I goes from 0 to n, and j goes from 0 to, I goes from 0 to m, and j goes from 0 to n. First, running the indexes j within each index I. So this is, I hope it's clear what sigma 1 prime is, and this is clearly a refinement of sigma 1 because I have the terms of sigma 1 in it, these things m1, m2, and this is actually mn. Okay, and in a similar manner we will refine sigma 2 using sigma 1. So now we'll refine sigma 2 using sigma 1. Let me just do it again just to give you the hang of it. So what we are starting with is the filtration sigma 1. So that is given by m equals m0 contains m1 contains all the way up to mm, which is equal to 0. And then what we'll do is we'll intersect it with nj. So what we get is nj equals m0 intersect nj contains m1 intersect nj contains mm intersect nj, and this is still 0. And now let's add nj plus 1 to each term of this series. So we get nj equals nj plus 1 plus m0 intersect nj. This contains nj plus 1 plus m1 intersect nj, and so on. And here we have nj plus 1 plus mm intersect nj, and this is equal to nj plus 1. So what we have is a new composition series which we will call sigma 2 prime. So sigma 2 prime, just like we had sigma 1 prime, it's a composition series given by we'll call it Nij equal to Nj plus 1 plus mi intersect nj. And now we first run over the index j, and within that we run over the index I. So 0 less than or equal to j less than or equal to n minus 1, 0 less than or equal to I less than or equal to m minus 1. More explicitly, what we are looking at is the composition series. So we start with m, which is equal to n0, 0, which contains n 1, 0, which contains n 2, 0. So the indexing, the order of the indexing here is reversed. And this is equal to n1. And then this is the same as n01, which contains n11, which contains n21, which contains, oops, this should be an n, m1, this is n2, and so on, all the way down to nmn, which is nn, which is 0. So this is a refinement of the composition series sigma 2. Now let's see what the quotients of these two series are. So the quotients of sigma 1 prime are, well, there are some zeros, but the remaining are of the form qij equal to mi intersect nj plus mi plus 1. That's the ijth term of the series sigma 1 prime. And then we must increase j by 1, because in this the variable j, the index j, is running inside the index I. And so we have mi intersect nj plus 1 plus mi plus 1. And those of sigma 2 prime are q prime ij equal to, or maybe I'll call it, well, should be, maybe I'll call this q1 and I'll call this q2. Yeah, that makes more sense. And these are mi intersect nj plus nj plus 1 modulo mi plus 1 intersect nj plus nj plus 1. So these are the quotients of the two refinements that we have constructed. The situation looks something like this. So the there are four relevant R modules in this. So just a schematic picture, you have mi intersect nj. This contains two submodules, mi intersect nj plus 1 and mi plus 1 intersect nj. And then we have here the smallest module which is contained in all these, which is mi plus 1 intersect nj plus 1. Now it turns out that both these quotients are coming from this picture. What they capture is actually you take this module mi intersect nj and you go modulo everything that comes from here. So let me just make that statement. So lemma is that there exist isomorphisms which I will construct in the proof. So we have this stuff on top, mi intersection nj, modulo everything that's below it, which means I must take mi intersect nj plus 1 plus mi plus 1 intersect nj. This quotient is isomorphic to both the qij, q1ij and q2ij. So this is isomorphic to, on the one hand, this guy, and on the other hand, this guy. Okay, and let's see how to prove this lemma. This is fairly straightforward exercise. So, so proof of lemma. What you do is, let's try to define an isomorphism for the modules on the left, and the other one will be quite similar, just interchanging the roles of m, n, I, and j. Role of m with n and the role of I with j. So what you do is, you have mi intersect nj. So let's define. So we have what? We have mi intersect nj, and this is a submodule of mi intersect nj plus mi plus 1. But that has a surjective map onto the quotient module mi intersect nj plus mi plus 1 mod mi intersect nj plus 1 plus mi plus 1. So this is the quotient map, this is the inclusion map, and let phi be the composition of these two. So we'll call this phi. And this phi will give rise to the isomorphism that we desire. We just need to check now all these things. So then what is the kernel of phi? The kernel of phi is all those things in mi intersect nj, which also happen to be in this denominator here. And this you can show without too much difficulty that this is isomorphic to, and I leave it as an exercise for you, that this is isomorphic to mi plus 1 intersect nj plus mi intersect nj plus 1. And so phi induces an injective homomorphism. Phi bar from mi intersect nj mod mi intersect nj plus 1 plus mi plus 1 intersect nj onto mi intersect nj plus mi plus 1 modulo, this thing here. So that is injective, and now we only need to check that phi bar is surjective. The image of phi bar is so phi bar is surjective just because phi goes on to this. The image of phi bar is the image of phi. Okay, so we need to check that this is contained in the image of this. But the point is that mi plus 1 plus mi intersect nj is contained in mi intersect nj plus mi plus 1 plus mi intersect nj plus 1. And so because of this, phi bar will be surjective, because you're going to get everything over here modulo this in the image of phi. In fact, what this shows is that phi is surjective and therefore phi bar is surjective. So what we have shown is that these two modules on the left are isomorphic, and as I said before, by interchanging the role of m with the role of n and the role of I with the role of j, you can prove that these two modules on the right here are also isomorphic. And so we have Q1 ij is isomorphic to Q2 ij for all I less than or equal to m minus 1. And then the remaining quotients are just 0 because, the last module in the composition series in each row is the first module on the right. And so what we have is you can just remove those by merging those terms. Therefore, sigma 1 prime and sigma 2 prime are equivalent, completing the proof of Schreier's theorem. And let me emphasize again that in Schreier's theorem there is no hypothesis. When we prove the Jordan-Holder theorem, we will need a hypothesis about the ring R or about the modules M and N. Here, this is a completely general theorem. So you can even look at rings where the composition series are finite, but the rings can admit infinite composition series like Z. So if you have any two finite composition series of Z, they will admit, we are always taking composition series to be finite, that's how we defined it, they will admit a common refinement. And not only does it say that such a common refinement exists, the proof that we've given of Schreier's theorem actually shows you how to construct this common refinement.